Hello everyone. Let's resume from where we left. In the previous lecture, we have been discussing a bit about this notion of group homomorphism that we have learned a couple of weeks back. I mean, last couple of weeks. And also, we have learned this dihedral group, and we have solved one exercise related to dihedral groups, and we tried to see that more general statement holds in the context of any group. Okay, this was a more general result, more general than what we have already seen in the context of dihedral groups. And then we learned this notion of quaternion groups and saw that this is a new group. I mean, this okay, in the sense that this is different from the groups that we knew earlier. By that I mean this is different from the groups of order 8 that we knew earlier. Okay, so this is different from D8. By different I mean this is non-isomorphic. Okay, this is also different from Z mod 8Z. Okay, you can try to show this. Okay. Uh, okay, and then we try to understand the okay, I mean this is a standard argument. Okay, so this is something that has been applied here and there. So once while solving this exercise, which shows that any infinite cyclic group is no different from the group of integers. By no different I mean that these two I mean are isomorphic. And then similar arguments were used in order to understand the set of all homomorphisms from Z to a given group G. Okay, a while before we decided to write hom G1 G2 to denote the set of group homomorphisms from G1 to G2. Okay, so this exercise 175 aims to understand hom Z comma G. Okay, for a given group G, and of course Z here denotes the group of this additive group of integers. Okay, yeah, and this argument I mean this again repeats something that you already knew, which is just about unwinding or unwinding this definition or the property that a group homomorphism captures, the key property of a group homomorphism. Okay, and then we try to revisit similar problems. Okay, for certain known groups. For instance, so in other words, we are going to make an attempt to understand hom G1 G2 for certain groups G1 and G2. So you have already made an attempt to understand this set when G1 is equal to Z, right? So now we'll focus on some other instances of G1 and some other instances of G2 also. Okay, so let's move on. So let's first make this remark, which is based on our previous observation, and that was an immediate consequence of the notion of a group homomorphism. Okay, uh, so this is I mean this remark says that if you start with a cyclic group G generated by an element little g, then whatever group homomorphism that one may think of, okay, whatever group homomorphism phi from G to G prime that one may start with, that is determined by the image of this element little g under phi. Okay, why is this so? Because whichever element that you may wish to pick from this group G, for instance if you pick an element H, then the group G, this group G being a cyclic group generated by this element little g, we know that H has to be a power of G. Okay, and then phi of H is no different from the nth power of phi G. More precise, with more details, one can see that phi of H is phi applied to G power n, and using the fact that phi is a group homomorphism, we see immediately that this is the nth power of phi of G, right? Okay, and yeah, so based on this observation, or maybe based on a variant of all this, okay, based on certain appropriate adaptations of all this, in other words, you just only need to use the defining criterion of a group homomorphism to see this fact that the set hom Z mod n Z comma G, that is in one-to-one correspondence with the set of all elements of G of order I mean of elements of G which satisfy this equality that G power n is equal to E. Okay, and this one-to-one correspondence can be obtained via this map which sends phi to phi of 1 bar. Okay. Okay, great. And as I remarked at the very beginning that one of the aims of one of the okay, so one of the first I mean, one of the aims of today's, I mean, of this lecture is to understand home G1, G2 for certain specific G1s and G2s. In other words, we are trying to understand homomorphisms from G1 to G2. So let's try to understand all the homomorphisms from Z mod 5Z to Z mod 7Z. Of course, as we discussed earlier, I think in this lecture notes that whenever we pick two groups G1 and G2, this home set that is non-empty. Why? Because you can consider the trivial map. So you could consider the trivial map. You could consider the trivial homomorphism. Trivial homomorphism sending all element of G1 to identity element of G2. So let's denote it by E2. Okay, so this is something that you have already discussed, and that shows that this home set, this home G1 comma G2 is non-empty. Okay, so of course, given any two groups, you already know that there is a homomorphism. So the task that this exercise provides us is to determine all the homomorphisms. Okay, so let's pick one such homomorphism phi. Okay, and let's make few observations. So 5 times 1 bar is 0, and you know that 7 times any element from Z mod 7Z is also 0, and one can continue the argument. Before getting into the argument, I just want to draw your attention to certain notations or certain notations that is used in the proof. For instance, 0 bar you get to see here, and 0 bar you also get to see here. Okay, so 0 bar has got two different meanings, of course. So when you look at the element 0 bar inside Z mod 5Z, then this 0 bar is different from the 0 bar that we have inside Z mod 7Z. Okay, so please be careful, and there is certain room for confusion, but if you follow things carefully and try to make sure that these notations are used consistently in a compatible and in a coherent manner, then there is no room for confusion. Okay, yeah, so first note that 5 times 1 bar is 0 bar. Okay, you may say that this equality alone doesn't seem to make much sense, because we do not know whether we are talking whether we're talking about this equality in this group Z mod 5Z or inside Z mod 7Z. So of course I have just I made it clear. So here we wrote that 5 times 1 bar is 0 bar. This holds in Z mod 5Z. Once you write an equality and indicate where it holds, then there is no room for confusion. Okay, and certainly you know that 7 times 1 bar is not 0 inside Z mod 7Z. Sorry, 5 times 1 bar is not 0 inside Z mod 7Z. That's a separate story. But if we just say that this is 0, there is certain room for confusion, and it's our responsibility to make sure that there is no room for confusion. So we need to say that this equality holds inside this group Z mod 5Z. Okay, and that automatically tells us that 5 times phi of 1 bar. Okay, so note that this 5 times phi of 1 bar means phi of 1 bar composed with itself 5 times. I wrote 5 dot because I know this group is additive, and this phi of 1 bar is an element of Z mod 7Z. Okay, yeah, so 5 times 1 bar is equal to phi applied to 5 times 1 bar. Okay, and so here we have an element inside Z mod 5Z, right? And that is equal to 0 bar, and phi being a group homomorphism sends the identity element to the identity element. Okay, so we have the 0 bar, so we have this equality inside Z mod 7Z. Again, note that this 0 bar is the identity element of Z mod 5Z, and this 0 bar is the identity element of 7Z. Okay, so as you see that there is some room for confusion, but again, if you follow carefully, you will see that things are completely consistent. Okay, great. And then and then you also know that 7 times phi of 1 bar is 0, right, inside this group Z mod 7Z. So here I did not write anything, because when you talk about phi of 1 bar, it is clear that we are talking about an element inside Z mod 7Z, right? So again, if you want to be precise, it's a good idea to write, at least when you are learning these notions of groups for the first time, it would be a good idea to write that this holds inside the group Z mod 7Z. Okay, anyway, so you know that this equality holds. So what you have observed is that 5 applied to 5 times phi of 1 bar, that is phi of 1 bar composed with itself 5 times, leads you to 0, and again the same element composed with itself 7 times leads you to 0. Okay, and now you can use the fact that 1 is equal to 15 minus 14. Okay, in other words, I am saying that phi of 1 bar is 15 times it's 15 dot phi of 1 bar. That means phi of 1 bar added with itself minus 15 times, phi of 1 bar added with itself 15 times, and then minus phi of 1 bar added with itself 14 times. Okay, that gives you phi of 1 bar, and this is equal to 3 times 5 times phi of 1 bar. This is 2 times 7 times phi of 1 bar, and you know that this quantity is 0, and so is this quantity, right? So you have 3 times 0 and then 2 times 0, that ends up giving you 0. Okay, so it follows that phi of x bar equal to 0 bar. Why is the case? Because we have just proved that phi of 1 bar is 0. Okay, and since 1 bar generates the group Z mod 5Z, it follows that phi of x bar is equal to 0. Okay, for any x inside Z mod 5Z, right? Since x bar is equal to 1 bar added with itself couple of times. Okay, so phi of x bar is equal to phi of 1 bar added with itself couple of times, right? And then that gives you 0. That uses the fact that the map phi that you have started with is a group homomorphism. Okay, so we have seen that whatever group homomorphism that one may start with, you will end up obtaining phi of x bar equal to 0 for any x. Okay, in other words, any group homomorphism has to be the trivial homomorphism. So the trivial homomorphism from Z mod 5Z to Z mod 7Z is the only homomorphism from Z mod 5Z to Z mod 7Z. Okay, yeah. And now one can try to extend this result. Okay, so let's assume that let's start with two non-zero integers m and n and try to find out all homomorphisms from Z mod mz to Z mod nz. Okay, yeah. So now note that homomorphism from here to here is determined by the image of the element 1 bar from Z mod mz, and the image of 1 bar here has to be an element which composed with itself m times gives you the identity element. Okay, this again follows from what you have just observed, that any map from Z mod mz to whatever group G that we might be given, this Hom set. Okay, in other words, any homomorphism from Z mod nz to G is determined by or rather kind of there is a one-to-one correspondence. There are two things together. Okay, so first is remark 176, and then is this remark 177. So for a cyclic group generated by an element G, that is determined by the image of one specific generator. Okay, a homomorphism is determined by the image of one generator. Okay, and that if you want to understand so thus if you want to understand the homomorphisms from Z mod nz to G, then you suffices to quote unquote it suffices to know that the image of the image of 1 bar under a given group homomorphism phi, and this map produces a one-to-one correspondence between this Hom set and the elements of G, which compose with itself n times, gives us E. Okay, compose with itself n times. So this n is the n that we have here. So now, just because you started with the group Z mod mz, okay, so you need to look at elements of of this group. Okay, so a bar of Z mod nz, so that a bar added with itself m times gives you 0 bar. Okay, of course 0 bar inside the group Z mod nz, inside this group. Okay, inside the target group. Great. So note that if you start with an element, an element of Z mod nz is of the form a bar. Okay, so this is the congruence module. This is the equivalence class of some integer a under the congruence modulo n relation, of course. Okay, and this holds for a unique integer a lying between 1 up to n. Okay, and then this equality is equivalent to saying that m a bar is 0. In other words, we are saying that n divides m a. Okay, and that is exactly that is equivalent to saying that n divided just let me elaborate a bit. So we have n dividing ma, and if we have an integer k, okay, if k is an integer and k divides both sides, okay, then of course n over k divides ma over k, right? This is this is just a kind of one line verification, okay, because you say that one integer divides some other if their ratio is an integer, okay. If they're, I mean, if you just divide this by this, I mean, if you consider this over this inside the rational numbers, okay, then this is an integer, okay. And now, I mean, from this hypothesis that k is an integer and k divides n and k divides maybe just let me write that this is a non-zero integer. That feels good. I mean, and also to be precise, we need to include this. Suppose we have started with a non-zero integer such that k divides n and k divides ma. Then these two then these two rational numbers are integers, okay, and the ratio is equal to the ratio of ma to n, right? And that is an integer. So it follows that n over k divides ma over k, right? So n over the GCD of mn divides m over the GCD of mn times a, right? And now note that these two integers have no common factor other than 1, okay. So it follows that this integer, okay, n over GCD mn, this integer divides a. So it follows that n over GCD mn divides the integer a. And now a, this integer a being being an integer between these two, 1 up to n, that is this a being an integer satisfying these two inequalities, it follows that, and also that a is divisible by this integer. It follows that there are following are the possibilities for the integer a, namely a can be n over mn, right? So a can be n over mn, it can be twice n over mn or thrice n over mn, and all the way to m over GCD mn times n over mn, okay. So we have reached this upper bound for a, okay. Great. So so just to remind you once again, we are looking for all the elements a bar of z mod n z. So we and we also recall that such elements, their one-to-one correspondence with the equivalence class of a unique integer is satisfying these inequalities, okay. So you're looking for integers a between 1 up to n such that this holds, okay, and this condition is precisely equivalent to this divisibility condition, right? So the integers a that you are looking for are exactly equal to this, okay. So we have established that the elements a bar of z mod n z satisfying this equality are precisely the equivalence classes of, in other words, the mod incongruence classes of these integers, okay. Okay, now we know that this Hom set, okay, the elements of this Hom set, they're in one-to-one correspondence with the mod incongruence classes of the integers, right? Because they're in one-to-one correspondence with the elements a bar of z mod n z, which when added with itself m times gives us 0, okay. So we have understood this set, Hom set, but at the same time it would be better to write down this homomorphism explicitly, okay. This for that we need to again use the fact that the one-to-one correspondence that we described or that we know of, okay, is given by this map which sends the homomorphism to its image at the element 1 bar, okay. So whatever I mean, so so here the one-to-one correspondence that we have, okay, under this one-to-one correspondence, when how to say, when this is further, when you kind of open it up, okay, using this remark, then you see that for any integer I among this list, okay, among this list of these many integers, okay, for any integer I, then there we have a homomorphism phi I from z mod mz to z mod nz that sends 1 bar to I bar, okay. And then you know that these homomorphisms are precisely all the distinct homomorphisms that one can have from z mod mz to z mod mz, okay. And here I varies in this set. Now of course once I specify this image of 1 bar under this homomorphism, then you know the images of the remaining elements, right, by this remark, okay. Because any other element of this group G, where G is z mod mz, that is generated by 1 bar, okay. Yeah, so I suggest you to go through all these arguments, okay. And here exercise 178 serves as a toy example of what we are doing here in exercise 179, okay. Yeah, and as you see also from this more general case, from this exercise 179, you see that there are exactly GCD-MN many homomorphisms, right? Oh, sorry. there are exactly GCD many homomorphisms from Z mod MZ to Z mod NZ, and in the previous example, we know that we had m equal to 5 and n equal to 7, that GCD is equal to 1, so you had exactly one homomorphism. Okay, and we know the trivial homomorphism is one homomorphism, so there is nothing else. Okay. Anyway, great. So here is an exercise that we have seen in the previous problem set, but this is an important one, so let me try to review it. Okay, this is something that you have already seen. Okay, please make sure that you understand this argument very well. Okay, because this is something that will appear over and over again, at least in this form or in some disguise or in a or some of its variants will keep on appearing over and over again. Okay, yeah. So this exercise tries to understand the subgroups of Z mod NZ, or specifically it tries to understand all the distinct subgroups of Z mod NZ. It says that they are in one-to-one correspondence with the divisors of n, more precisely with the positive divisors of n. Okay, so if you take a positive divisor d of n, then the subgroup of Z mod nz that is generated by the mod incongruence class of D. Okay, sorry, for I need to reformulate it a bit. So if you take a positive divisor d of n, then if you look at the subgroup of Z mod nz generated by the mod incongruence class of the integer d, then you get all the distinct subgroups of Z mod nz. Okay, so here you need to run d over the set of all positive divisors of n. Okay, and this is again a simple application of division algorithm, and this is a simple application of division algorithm. This is also a usual application of division algorithm. Okay, the idea is to start with a subgroup of Z mod nz, and then you pick the smallest positive integer whose mod incongruence class is contained inside H. Okay, and then you take some element from H, and then you apply the division algorithm to the integers b and a, so you end up getting a quotient and a remainder. So we express b as qa plus r, where r is an integer between 0 up to a minus 1. So one can do all this because you started with a positive integer a. Okay, and certainly b is an integer. So we have b bar equal to qa bar plus r bar, and you know that a bar is an element of H, and again b bar is also an element of H. So b bar minus qa bar is an element of H2. So you end up getting that r bar is an element of H. Okay, and r satisfies this inequality. On the other hand, a is the smallest positive integer, such that a bar is contained inside H. So it follows that r has to be equal to 0. Okay, and once you show that r is 0, it follows that b equal to qa, and then so you see that whatever element b that you chose from H, that whatever element b that you b bar that you chose from H, that can be obtained from a bar. Okay, in other words, if you look at the smallest positive integer a, such that a bar lies inside H, then you will see that a bar also generates H. Okay, so we have seen that H is generated by a bar, where the integer a satisfy this property. Okay, and now you know that n bar lies inside H, right? Why is that the case? Could you think? Because n bar is 0 bar, right? And H being a subgroup, it has to contain the identity element of Z mod nz. Okay, so 0 bar, that's again same as saying n bar, so n bar has to lie inside H. Okay, and again, so it follows that a has to divide n, right? I'm sorry, yeah, because we just repeat the same argument. Okay, great. So you see that a divides n, and the Z mod nz, the integer a that you have chosen, that integer a is a divisor of n, right? And those a subgroup of Z mod nz is generated by d bar for some positive divisor d of n. Okay, and here d is characterized by the following property, that it is the least positive integer such that its congruence class lies inside this subgroup H. Okay, and now if you take two distinct positive positive divisors d1 and d2 of the integer n that you have started with, and then if you look at the subgroup of Z mod nz generated by d1 bar and the subgroup generated by d2 bar, then it follows that they're distinct. Why? You can look at their order, okay? The sizes of these two subgroups. The first subgroup is the subgroup generated by D1 bar, and the second one is the subgroup generated by D2 bar. You will see that they have got different orders, okay? That you can see, and that you can see, and you can also show, okay? So this proves that the subgroups of Z mod nz generated by D bar, where D runs over the positive divisors of n, they are first of all the subgroups of Z mod nz, and that they are the distinct subgroups of Z mod nz. Okay, so we have established this statement. Okay, yeah. Okay. Yeah, once you have done this, maybe let me try to review something we have already seen. Okay, so let's recall that if we start with a subgroup H of a group G, then we have already learned the notion of left cosets of H in G and the right cosets of H in G. Okay, and yeah, so this lemma indicates that if you take the set of all left cosets of H in G, and if you take the set of all right cosets of H in G, then there is a one-to-one correspondence between these two sets. Okay, and as a consequence, there are several consequences of this lemma. One of the first consequence is that these two sets, they are of same cardinality, right? If there is a one-to-one correspondence, right? So the number of left cosets of H in G is same as the number of right cosets of H in G. Okay. Yeah, and of course, okay, let me explain the proof. But if you like to think about this lemma on your own, then just do not take a look at this proof, or do not listen the proof that I am going to discuss right now. Try to work on this lemma on your own, okay, at least for a while, and then if you need certain inputs or certain ideas, then please feel free to go through this proof and listen to what I'm going to explain. Okay. Great, but this is the lemma that you should be able to establish on your own right now. Okay, it may take a while, so please work on it. Please think. Okay, yeah. So let me try to explain the proof of this lemma. So just for simplicity, we just introduce few notations. We denote the set of all left cosets of H in G by this letter L, and the set of all right cosets of H in G by this letter R. Okay, and now we consider a map from L to R, which sends the left coset GH to the right coset AG inverse. One of the first question that may arise in your mind is that why not the map GH to AG? So please think about it. Okay, so this is an exercise. Yeah, so now let me get into the proof. So we send the left coset GH to AG inverse. Okay, and now the very first task is to see that this map makes sense. In other words, that this map is well defined. So suppose the point is that GH can also be maybe G naught H, or maybe it can also be G prime H, right? And then we're just choosing some representative of this coset, and you're sending this coset to H times the inverse of that representative. In other words, you're choosing a choosing an element from this left coset, and you are sending it to the right coset of H corresponding to the inverse of that representative, or that element of that coset. Okay, so now it indicates that it depends on the choice of the representative, okay, or choice of the element from this coset. Okay, yeah, so G could be a representative, or G prime can also be a representative, right? So in other words, we can have two elements G and G prime of the group G, which are related as follows: that G is equal to G prime H for some element H inside H. Okay, and that implies that this element G inverse is H inverse times the inverse of G prime. Okay, and that shows that H inverse is H, and then H inverse and then G prime inverse, and if you multiply H by H inverse, you end up getting H. Okay, this follows from the properties of a subgroup. Okay, and this is easy to see. Okay, so H inverse is equal to H, and then you end up getting H times G prime inverse. So H inverse is equal to H G prime inverse. So you have established that this map is well defined. Okay, and also note that this map is injective. Okay, that is not much different from repeating this argument or suitable modification of this argument. So let's go through. So you start with two left cosets g1h and g2h and assume that their images are the same under this map. So you're assuming that hg1 inverse is same as hg2 inverse. So you're assuming that g1 inverse is h prime times g2 inverse, and then again by not by the same argument but by a similar argument, it follows that this left coset g1h is same as the left coset g2h. Okay, so it follows that this map that you have started with, okay, is well defined, and then it follows that this is injective. And now for the surjectivity it is clear, because whatever right coset that you may have, there's a typo here. This is the image of the left coset, certainly not gh in general. So I should write g inverse h. Okay, so whatever right coset hg that you may start with, that is the image of the left coset g inverse h under this map. Okay, so this map gh going to h inverse, there is a bijection from L to R, and so we have proved that the set of left cosets of h in g and the set of right cosets of h in g, they are in a one-to-one correspondence. Okay, and that suggests us to introduce one notion, okay, or a notation. So if you look at the number of cosets of h in g, okay, or maybe number of distinct left cosets, okay, and which is same as the number of distinct right cosets by this lemma. So one can look at the number of distinct left cosets of h in g, and usually, this is known as the index of h in g. So if you start with the subgroup h of a group g, then the index of h in g, so this is defined to be the number of distinct left cosets. You can also define it to be the number of distinct right cosets, right? Because we have this lemma which says that these two numbers are the same, and this is, this index is often denoted by g colon h within brackets, within square brackets. Okay. Yeah. So again, as I said, we'll be trying to recall some of the notions that we have already seen. So we have recalled a bit about we recalled a bit about the notion of cosets, and now let's try to review Lagrange's theorem more precisely. Let's try to review, or rather recall, certain steps of the proof of Lagrange's theorem. So if you go back to the proof of Lagrange's theorem, you will see that we have actually shown that for a subgroup H of a finite group G, the order of G is equal to the product of the order of H and the index of H in G. Okay, actually we have proved that, the proof that we have presented, we have shown that the order of G is equal to the product of the order H, the product of the order of H, and the number of distinct sorry, there is not much space. And the number of distinct I think left cosets, and I left it as an exercise to to use this right cosets in order to have a different, an apparently different proof of Lagrange's theorem. Oops, this is not on H, this is in H. Sorry, in G, Yeah, so you have shown that the order of G is equal to the product of the order H and the number of distinct left cosets. In other words, is equal to the product of the order of H and the index of H in G. Okay, so this order of G, okay, maybe I should tell you something that here this denotes the order of G. Yeah, you may know that if you have a set S, then its cardinality is sometimes denoted by S within these two vertical lines. Okay, this denotes cardinality of S. Okay, so if you start with a group, if you start with a group G, then if you look at its cardinality, then by definition this is the order, right? So order of a group G is the cardinality of G. So here size of this here by this notation it denotes the order of G, and similarly this denotes the order of H. Okay, great. Then so we have proved, so in the course of proof of Lagrange's theorem that you have presented, you have showed that order of G is equal to this times the index of H in G. In other words, the index of H in G is equal to the ratio of the cardinality of G, or the order of G and the order of H. Okay, it's the ratio of the order of G to the order of H. Great. And yeah, so you have a remark, you can try to show this, that for any non-zero subgroup of Z, okay, that is generated by its index in Z. Okay, so just read this statement at least a few times, and with some with some how to say, with some care, and then you'll see I mean, you need to first see the content of this statement, and then you can try to prove it. Okay, once you understand the statements, the proof will follow immediately. Okay, so let me conclude it here.